Good morning, everyone. Welcome to the course on data structures and algorithm. In this video, we are going to talk about the introductory part of linked list. Now, linked list is a basic example of a dynamic memory allocation. So before we understand what is dynamic memory allocation, we need to understand what is static memory allocation. So this is a very simple examples of static memory allocation is array that we have already seen in our C programming course. So let's start exploring it. So what is static memory allocation? So you can see this is a very simple initialization and declaration of array. Array having, let's say, maximum size 10 and having 5 different elements, 35 to 71. So we know that array starts from 0 and it goes all the way up to, for example, in this case, up to 4. So now I'm showing the same stuff over here. So marks, that's array name. Then these are all the locations or positions, 0th position, 1st, 2nd, 3rd, 4th, and these are all the values which are stored on the respective locations. So at the 0th position we have 35 stored, at 1st position we have 89 stored, and likewise. So this is a simple declaration and initialization of an array. Now you can also visualize the same stuff in other way, like these are all the variables that we are having. So because in array we identify the location by the index, so marks 0, marks 1, marks 2, marks 3, and marks 4, and then these are all the values. So at marks 0 we have 35 stored, and marks 1 we have 89 stored. And let's assume that these are addresses, because in main memory every location is identified by a unique address. So let's assume that integer requires 2 bytes of memory. Alright, so for that, let's say this one is the address of very first element is, let's say, 1000. So 1000 and 1001, sorry. So these two elements, 1000 and 1001, these two elements are reserved for mark 0. Same for next 2 bytes, 1002 and 1003. 1002 and 1003, these 2 bytes are reserved for marks 1. Same way, next 2 bytes, 1004 and 1005, these 2 bytes are reserved for marks 2. Then for marks 3, again 1006 and 1007, and for last element marks 4 we have 1008 and 1009. So in short, every location in the main memory is having a unique address. So these addresses are very important so far as dynamic memory allocation part is concerned. So we'll be talking about these addresses later. Now let us try to see what are the problems with static memory allocation. Means, suppose if you wish to insert any element in an array, so what will exactly happen? For example, the same array is over here and I wish to insert, let's say, 11 between 89 and 67. Okay, this is a very simple application wherein I wish to insert an element in an array at specific position. Let's say this is 0th, 1st, 2nd, 3rd, 4th. So I wish to insert after 89, means at this particular location on the position number 6. So what would I do? How can I insert 11 after 89? So for that I need to move all the elements to one position right, and I need to create a space, a hole over here. I need to create. So 67 has been moved, 83 has been moved, 71 has been moved, and then and I will not be moving all the elements which are prior to this particular location, but I'll be moving all the elements which are after this particular location. So 35 and 89 will remain as it is, and whatever space I have created, in that particular space I'll be putting that the 11. So this is how normal insertion is done. So 11 I'll be putting over here. So this process looks very simple. Yes, it is simple, but where is the problem? The problem is, for example, over here n equal to 5. We have only 5 elements, so the total number of shifting over here are, let's say, 3. Shifting are 3. But what if this n equal to large number? What if n equal to, let's say, 5,000 elements? What is n equal to, let's say, 1 million elements? All right. So in this particular case, if n equal to 1 million, how many shifting are required just for inserting one node? So you can think of, the computation power or the wastage of computation power in this case. So this is not a good idea, like shifting all these elements just for the sake of inserting one particular number is not a good idea. Let's take the deletion part. How does deletion happen? So for example, in the same array I wish to delete 67. So deletion is basically overwriting in computing. So if I wish to delete 67, what I'll do, I'll overwrite 67 by 83 and I'll overwrite 83 by 71, and the other two elements will remain as it is. So this is how the 67 is deleted. And again you can see the overwriting is nothing but shifting operation. So again the same problem will happen for small number of m. This is okay, but what if the total number of elements are 500, 1000, 10,000, 100,000? So in those cases, definitely, deleting a single node will require lot of computation power. So these are the problems with static memory allocation, and which motivate us to think of something different, and that something different is dynamic memory allocation, which will be implemented through linked list. So with this basic idea about why do I really need the concept of linked list, let us formally define what is a linked list. So basically it's a linear data structure like queue and stack. This is also linear, means it goes in a line. Okay, like it has linear means it has the adjacent neighbors, it has left neighbor or right neighbor, something like that. So it is a linear data structure consisting of group of nodes. So what is node? I'll tell you in a little while. Supposing these are all the nodes that I am having in the particular linked list. So I can have n number of nodes, no problem. Okay, so these are group of nodes. So you can have a group of, for example, in this case I have drawn 6 nodes. Okay, or you can have 60 nodes, or you can have 6,000 nodes. So group of nodes, that's the second thing. Now where each node points to the next node. Now this is important because there is, in case of array, we have connection between two numbers by the index, because in array we know that marks 0 is nothing but the 0th element and marks 1 is nothing but the first element. So I do not need to explicitly specify the linkage, the address between these two particular element, but it is not the case with linked list. In linked list we need to connect two adjacent nodes. We need to have some sort of connection between two neighboring nodes. So how does it work? In every node I'll be having a space which will be a pointer. In every node I'll be having a space which will be a pointer. And for example, let's say these are all the addresses, 1000, 2000, 3000. These are just sample addresses, example addresses. All right, in real situation the addresses would not be in this sort of unique numbers and shorted numbers. I'm just taking for the sake of understanding. So if I wish to point, like if my first node, if I want to connect my first node with the second node, I'll be putting address of second node over here in the pointer part of first. So that means now it is pointing to the second node. Alright, if I wish to connect my third node with the second node, so I will be putting the address of third node in my second node. If I wish to connect the fourth node with third node, I will be putting this 4000 as part of my third node. Likewise this one, likewise this one, and for the last node, because there is no node after it, I will be setting it as null. So each node is comprising of two elements. Now you can see that each node is comprising of two elements. like one is data. You can see this is your data. Data could be anything, like it could be age, it could be name, right? So you can have a data like 10, 29, 56, 79, minus 8, 44. So you can have one element as data and other element as a reference or a pointer or a link. So other element is your link, which is pointing to the next node. So to the next node in the sequence. So this is how you can see that the entire concept of linked list is explained in a very simple terminology. Again, linked list is basically a linear data structure, means every node is having two adjacent node, the neighbors, except the first and last one, because in first there is no previous node and in last there is no next node. So except first and last, every node is having adjacent two neighbors, the previous neighbor and the next neighbor, previous neighbor and the next neighbor. So that's why it is called linear data structure, and it is comprising of group of node. As I said, in this particular part there are 6 particular nodes. It could be 600, it could be 6000, and every node is comprising of address of next node, and 2 different members are there with every node. One is data member and other is address member. So with this, if I again quickly read this definition, a linked list is a linear data structure consisting of group of nodes where each node is pointing to the next node by means of a pointer, and each node is composed of 2 parts, the data part and the pointer that we were talking about. So with this basic introduction or definition of linked list, let us now try to go for understanding how can we create linked list. So in this case, let's start defining dynamic memory allocation. So in case of dynamic memory allocation, so you can see the same linked list has been created with some addresses. Let's say 1000 is the address of very first node, then 1002, then 1003, then 1006. So these are all the addresses, and I am having this 5 different nodes. So the address of second node, which is 1002, that I have put it over here. The address of third node, I have put it in the second node. The address of fourth node, I have put it in the third node. Address of fifth, I have put it in the fourth node. And because now the fifth node is the last one, I'll be putting null in the address. So with this one, now let's see that basically a node is comprising of 2 members, as we have just said, the data member and the address member. So these all are data, all right. So these all are data, whereas the other part is what? The address of next node. So you can see this is address of the second node, this is address of the third node, address of the fourth node, address of fifth node, and this is null address. So every node is comprising of 2 member, data member and the address member. So now with this one, let's move further. So let us try to understand the insertion operation that we did it in case of array, in case of static memory allocation. So in case of static memory allocation, in case of array, we know that for inserting a single element, we need to make a lot of shifting. But in this case, supposing I wish to insert something between 89 and 67. I wish to insert something between 89 and 67. So all I need to do is, supposing this 11 is something I wish to insert between them. So all I need to do is just adjust few pointer. Rather than 89 pointing to 67, what I will do, I will make 89 point to this 11 and I will make 11 point to 67. So just by making 2 different pointers, just by setting 2 pointers, you can see that the complete insertion is made, and all other nodes like these nodes and these node, I do not need to touch them, all right, because all you need to do is insertion requires just setting up couple of pointer rather than 89 pointing to this. What do? We make 89 point to 11 by by putting the address of 11 this particular node, by putting the address of this node over here, and the address of 67 will be put over here, and that's done. So this is how you can simply insert any element in the linked list without affecting the entire linked list. So if there are 100,000 nodes in the linked list, you are not going to touch any of them except those two nodes in between which you wish to insert the element. And let's talk about deletion also. Supposing I wish to delete 67, so in that case also, because the earlier 89 was pointing to 67. How? Because 89 had the address of 67 in it. That's why 89 in. So rather than that, what you can do, simply you can put the address of 83 over here. So address of 83 is 1006. So the moment you put 1006 over here, that means now this is pointing to this one, and this node is no more the part of the linked list. So later on you can always free the memory. We will see that in later part. So this is the simplest thing. In deletion also, you do not need to touch this one, you do not need to touch this one. But if you remember, in case of arrays, in case of static memory allocation, if you wish to delete a specific element, you need to make lot of shifting. Over here, no shifting. Whether there are 5 elements, whether there are 500 elements, whether there are 5,000 elements, the same process will be carried out. So these are the benefits of dynamic memory allocation. Now let's move further. So formally, let us see the difference between dynamic and static memory allocation. So static memory allocation, we allocate the memory at compile time, means before running. So that means if you write integer marks, let's say 10, and every integer, if it requires 2 bytes, so 2 bytes multiplied by this 10 elements, that means total 20 bytes will be reserved in advance before running the program. Now whether if you use all 20 bytes or not, these 20 bytes are given to you, that's it. So if you are using all 20 bytes, that's great, but if you are not using 20 bytes, then you need to it will be resulting into wastage of memory if you are not using them all. Alright, so in case of dynamic memory allocation, we will not be allocating memory in advance, but we will allocate the memory during runtime, means as and when required, during the runtime. So this is the best part of dynamic memory allocation, because sometimes you do not know in advance that how much memory I am going to be needing. So in that case, dynamic memory allocation is very good concept for you. So over here in static memory allocation, maximum size is fixed. Like if you write integer, let's say marks 10, so this 10 is fixed. All right, you cannot reduce it, you cannot increase it. All right, so out of 10, if you are using let's say 8 elements, all right, then in that case 2 elements will be wastage. Out of 10, if you are using all 10 elements, then wonderful, 100% utilization. But out of 10, now if you want, let's say 12 elements, okay, but you cannot use because it cannot grow or it cannot shrink. So increase or decrease in the size is not possible, so it is fixed. Whereas in case of dynamic memory allocation, it is flexible. You can increase as well as decrease the number of elements in the linked list. Alright, the example of this is array, and the example of dynamic memory allocation is linked list. And what are the benefits and disadvantages? So with array, the benefit is the faster access, because for accessing any element, for example, if I wish to print marks 5, so you can simply write like this, marks 5, or if you want to print marks 100, you can print something like marks 100. Means you do not need to traverse, just specify the index and done. So it is having the faster access. All right, but the disadvantage, as we have seen, the insertion and deletion will result into very slow performance, and of course waste in memory. So these are the problems with array. Whereas in case of dynamic memory allocation, or you call it linked list, in that case the benefit is what? So insertion and deletion would be very fast, irrespective of total number of elements, whether there are 5 elements or 5 lakh elements, and it will result into saving in memory. Whereas disadvantage is slow access. Why? Because if you wish to go to, let's say this is a very simple linked list with 5 elements. All right, now every time we start with the very first element. Okay, so we start with this particular element, and let's say pointer is this, and if you wish to come down over here, you will have to traverse through all these elements. You cannot directly jump here, it is not possible. So linear access is very slow, and it will result into some computational overhead. You need to just keep on checking whether this is the last element, last element, last element, last. So there are a lot of ifs required in the program. So this is the disadvantage of dynamic memory allocation. Now with this one, let's talk of what are the different types of linked lists. So the very first one is singly linked list. For example, there are 5 nodes, and the address of first node is address 1, second node is address 2, address 3, address 4, and address 5. We are just taking randomly. So address 2, second node, will be put in first node. So address 2, that means now the first node is pointing to second node. Address 3, address of third node, is put over here as part of the second node. That means second node is pointing to third node. Address of fourth node is put as part of address of third node. So that means third node is pointing to fourth node. And address of last node is put in the previous last. That means this fourth node is pointing to the last node. And because there is no node after the last node, we are not putting anything, we are putting null in the address part. So this is called singly linked list. Okay, it is a one-way linked list. You can start from the very first one and you can go all the way up to the last one. These you cannot go back, means you can always go from D1 to D2, from D2 to D3, from D3 to D4, but you cannot go from D4 to D3 or likewise. So this is what you call one-way linked list, wherein traversal from left to right is only possible, the other way is not possible. So second is the circular linked list. In case of circular linked list, the only change is over here. Rather than making the last node pointing to null, because after last node there is no node, so we are making it null. Now rather than that, we will be assigning address of very first node in the pointer of last node. Okay, that means now this last node is pointing to first node, and now this is something like a linear list. So it's a circle, that's why they call it circle. So it's, if you traverse through this linked list, it will be an infinite traversal. There is no end over here, there is no null over here. So we will see in the programming part how to implement circular linked list and all this stuff. Next comes the doubly linked list. Now in doubly linked list, with every node you have 2 pointers. First pointer is pointing to the next element, and the second pointer is pointing to the previous element. And of course the data is there, with as we had in earlier case. So now in previous case we had only 2 members, data pointer and the next pointer. But now you have 3 members, data member, next pointer and previous pointer. Okay, so with this, let us try to understand. Suppose address of this is A1, address of second node is A2, address of third node is A3, address of fourth node is A4. So in this case, the first node, the next part of first node contains address of second node. The next part of second node contains address of third node. The next part of third node contains address of fourth node. And because now there is no next after this fourth, we are setting this next pointer of last node equal to null. Same way, if we talk of the previous part. So previous part of this last node, contains address this A3. That means it is pointing to the third node. The previous part of third node contains address of second node A2. That means it is pointing to second node. And the previous part of second node contains address of first node. That means it is pointing to first node. And the previous part of first node, there is no previous before the very first one, then it is set to null. So in this way, what is the benefit of doing this? In earlier case, we could traverse in one direction only. Now you can traverse in this way, or you can traverse in this way. So you can go to next, or you can go to previous. So this is the benefit of having doubly linked list. And last category is doubly circular linked list. So rather than assigning the next node of last and the previous pointer of first, what do? We are going to put address of very first node in the next part of last node. Again I repeat, we are going to put the address of very first node A1, into the next part of last node. And same way I am going to put the address of very last node A2, A3, A4. So address of very last node is A4. So I am going to put A4 in the previous part of first node. Now that means now first node previous is last and last node next is previous. So this is doubly plus circular linked list. Now there is no null pointer over here, right? So in our next videos we will be talking about the implementation part of this doubly and circular list. But in this particular video we will be talking about how to create a simple singly linked list. So let us talk about that, how to create. So for that, as we know, every node is comprising of two members, data member and address member. So every node, supposing I am having three members, so all the three members are having this 10, 20, 30 as data members, and I have not put anything. For example, addresses are 1000, 2000 and 3000, and data member for first is 10, 20 and 30. Now I wish to create linked list. So what I'll do, I'll put the second address of second node, that is 2000, over here. So the moment I put 2000 over here, that means it is pointing to this whole second node. Now if I put address of third node, which is 3000, over here as part of second node, that means now this is pointing to third node, entire third node. And because there is no node after this, I'll be putting null over here. Alright, that means there is no node after the third node. So now you can see this. So I have put 2000 over here, that means it is pointing to second node. I have put 3000 over here, that means it is pointing to third node, and now this is null. So now let us try to create, and the very first node will have separate pointer, like you can have start or you can have begin, you can give any name. All right, so from where we will be starting navigating the entire linked list. All right, so how do we declare it in our structure? So I'll be giving any name. Let's say I have given the name node. All right, so you can give any node, no problem. So it's node structure with two members, the first member is data, whereas the second member is the pointer. So first member is data and second member is pointer. So it's a star. We know that we have seen in our C programming, star next means pointer. So it's a next is a pointer. So the variable name, again you can have any variable name, no problem. But over here we have used data and next. So next, and because it is going to hold address of same type of structure, like node type of structure. So I am writing struct node over here. That means now next is a pointer which is going to hold address of node type of structure, and the first member is simple data. So this is how we declare a structure. Now how to create a node, how to create this node. Alright, because declaring a structure would not reserve any memory. Alright, so for that we need to write a statement like this. Alright, for that there is a function called malloc. There is a function called malloc. Malloc stands for memory allocation. Memory allocation. So it will, supposing you need a block of 10 bytes. Alright, so what you will do, you will specify that number malloc 10. So it will give you a 10 byte block. It will give you a 10 byte block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will give you a 10 byte block in memory, right? But over here I don't need 10 byte block. I need a block which can hold, you know, these two members, a data member and a pointer member. So for that there is a operator called size of. So size of will return. So I'm going to specify node type of structure. So now node is having two members. Let's say the integer requires 2 bytes and pointer requires, let's say, 4 byte, for example. Then so 2 byte plus 4 byte total is 6 byte. All right. So this size of function will return 6 bytes. 6 bytes. So now the malloc function becomes something like this: malloc in bracket 6. So it will reserve 6 byte block. 6 byte block in memory, like 2 byte for this data, 2 byte for data, and 4 byte for this second member, that is the pointer next. So it will reserve 6 byte over here, and the pointer to this entire block would return into some variable. Let's say in this case we are catching the address over here in new node. So now this new node is pointing to this newly created block. And how do we access this particular element? So we access like new node arrow hyphen greater than new node arrow data. And how do we access this one next? So new node arrow next, new node, that is the pointer, and hyphen greater than this is arrow next. So this is how you access the members of that particular block. So now if we read something like enter data, so new node equal to struct node star, that means node is created and it is being pointed by new node. And suppose if we read something enter data, and let's say if I enter 99, all right, where it will go? New node arrow data. So new node arrow data, so it will go over here. And now new node arrow next null. So now I have set it null. So this one particular node has been created over here. All right, I have set the data also, new node arrow data. This one is new node arrow data, and I have set the address also. So this one is new node arrow next. So this is how I create the new node, means a structure, and I put values into it. Now let's move further. So this thing is done. Now I am using 3 different pointers over here: start, new node, temp. So start is something which will be fixed. For example, if I am having at the end, if I create such kind of linked list, all right, so it will be something first pointing to second, second node pointing to third, third node pointing to fourth, fourth node pointing to fifth, and fifth mid. So in this case, start will always be pointing to the very first location. All right, and why we are setting it null initially? Because initially there is no node in the linked list, so initially start equal to null. So start equal to null indicates empty list, means there is no node. Later on we'll be using malloc to create different nodes, but right now it is empty list. Then new node is what? Every time when you create a node, the pointer used will be new node. Alright, so supposing you are creating this second node, so pointer will be used new node. Supposing next time you are using creating third node, the pointer will be used is new node. So new node is a pointer that is used at the time of creation. And third is temporary pointer. So if you wish to traverse, like if you wish to print all the element 10, 20, 30, 40, 50. So I need one extra variable which starts from that particular pointer will be starting from this location. Temp equal to start. You can start from temp equal to start. So very first location, and then you can keep on changing temp. You can keep on temp equal to temp arrow next. So you can keep on changing temp, because if we use start, what will happen? If we move start from here to here, if we move start from here to here, then we will lose the beginning of the list. So we are not going to move the start pointer. We will be keeping it fixed. We will be moving temporary pointer. Alright, so this is the basic idea. Now let us see how do we create a singly linked list. So every time new node equal to struct node star malloc. So suppose first time I am creating this one. So new node is this one. New node is equal to, I have created the structure. Now enter data. Suppose if I am entering 10. So new node arrow data. This one is new node. This one is new node arrow data and new node arrow next. Now check new node arrow next equal to null. So let us set it null. Now if start equal to null, yes, because this is the very first element. At that time start equal to temp equal to new node. So this is also start, this is also temp. Everything is this because this is the only element in the list. Now this is done, so it will not go in else. Now check this out. Do you wish to continue? Yes or no? Suppose I wish to continue. So it will again go here and it will create a next element. Alright. So it will create a next element, let's say new node. So the moment now this new node is used over here, okay, now I can erase this new node. Alright. Now the thing is, second time let us ask enter data, and suppose if you enter 20, then new node arrow data equal to 20 and the new node arrow next is equal to null. Let us set this also null. Now if start equal to null, no, this time start is not equal to null because it is pointing to the very first location. So in this case it will enter in else part, it will not go in this part. Alright. So temp arrow next equal to new node. What is new node? Let's say this one is 2000 and this one is 1000. So new node is 2000. So temp arrow next, which was earlier null, that will be now 2000. So now if I put that stuff over here, if I erase this one, then I can put the 2000 over here. So this new node is 2000, that I am putting it into temp arrow next. So now temp arrow next means now this is pointing to, and temp equal to new node. So 2000 I am going to put it in temp. So earlier temp was 1000, now temp I am moving to the next one. So now I can erase temp from this particular place. Right. So now this is the situation. Now this is the situation over here. So if I again move forward, let's say do you wish to continue, and if I enter yes, then again new node equal to struct node. So again a third node will be created and the pointer will be new node, and the moment I use new node for third one, so the previous I can erase. So I can erase the previous one. Alright, and then let's ask for data, that enter some data. So I am entering, let's say 30. So new node arrow data equal to 30. So new node arrow data equal to 30 and new node arrow next equal to null. So new node arrow next equal to null. Now check this out, start equal to null. Now this will not be true. It will be true just for first time only. When the very first node was created, start was null. That's it. Otherwise we will not be checking it. So now go to this else part. So temp arrow next equal to new node. Suppose the address of this node is 3000. So new node equal to 3000, and that I am going to put it in temp arrow next. Temp is over here, whose next is null. So now it will not be null anymore. Alright, and now it will be 3000. Now it will be 3000. So now this is 3000. That means now this is pointing to this. And temp equal to new nodes. So now earlier temp was 2000. Now 3000 is assigned to this. So now this temp is gone. Now temp is pointing to this one. Alright, so this is how now I can erase the temp. Now I can erase this temp. And now so it is pointing here, and same way you can just keep on continue the things. All right, and you can have fourth node, you can have fifth node, you can have sixth node, so it will keep on continue. But you can see the start is pointing to the very first node. Every time new node will be the pointer to the new node generated, and temp will be pointing to the last node created. That's it. All right, so now what if I wish to print everything? What if I wish to print 10, 20, 30? So I can start from this particular pointer. I can begin from this pointer start. And what I'll do, I will not move start, because if I move start, what will happen? I will be losing the reference of very first node. So what am I doing is, I'm using the same temp. So now I'll be moving this temp from this to this position. Alright, so temp I can move here because it's a temporary pointer, and then I can have temp arrow data printed. Temp arrow data. So what is temp arrow data? Temp arrow data is 10, and then what you can do, you can move to temp equal to temp arrow next. So what is temp equal to temp arrow next? Temp arrow next is, in this particular case, it's 2000. So 2000 is assigned into temp. So now temp is moved to second place. Now again you can repeat this in a loop, these two statements. Then again print temp arrow data, so it will be 20. Again temp equal to temp arrow next, so it will be 30. Just keep on repeating until what? When you encounter this null. So till that point you can keep on moving. Alright, so that is my last part, display. So in display, I'll be starting temp equal to start, and while temp is not equal to null, I'll be printing temp data and I'll be moving temp to the next location. So whole this thing will be repeated, and 10, 20, 30, 40, whatever members are there will be printed. So these three different modules, if I combine them together, so this is my structure definition, then this is my loop, and this is my printing part. Alright, so this will be output. Enter data. First I enter 10, then I ask, do you wish to continue? Yes. 1 for yes. Then if I enter 20, then it will ask, do you wish to continue? Yes. Then if I enter 30, then I'll ask, do you wish to continue? No. 0 for no. Then it will print, this particular logic will print 10, 20, 30. So this will be the output. Now you can see this link, the whole program is given over here in this link, and that is also available in the description part. So if you wish, you can go through that program. And with this I conclude this video on introduction of linked list. In the second video we will be talking about insertion into the linked list. Thank you very much all of you for being with us.